guys, let's talk more about Lewis structures and the exceptions to the octet rule. So you are going to see three types of exceptions. The first one is ions or molecules with an odd number of electrons. These are generally highly reactive species, just like nitrogen monoxide. So nitrogen monoxide is NO. We know that nitrogen is right here in the periodic table, is going to have 5 valence electrons. Oxygen is right here, is going to have 6 valence electrons. So that's a total of 11 valence electrons. So we cannot actually draw all the electron pairs that we usually used to. So even if I draw out the structure, I know I will need a double bond between the nitrogen and the oxygen atom. I used 4 electrons so far. So I still have 7 electrons to put those around the nitrogen and the oxygen atoms. And I can, let's say, satisfy my oxygen atom with the octet rule to have 8 electrons around it, but now I only have 3 electrons left to put on the nitrogen atom, and well, nitrogen doesn't have the 4 extra electrons that it needs to satisfy the octet rule. So when you have odd number of electrons, you actually cannot draw valid Lewis structures. This is an example that you are not going to see that often. The 2 other exceptions are way more often occurring. So there are ions or molecules with less than an octet, and ions and molecules with more than 8 valence electrons, or expansion to the octet rule. So let's start with the less than an octet. In these cases, we are going to have the central atom from the second period, but before carbon. So if we look at the periodic table, this is the first period. We know that hydrogen and helium can have a maximum of 2 electrons because we are filling up the first s orbitals. In the second period, we are filling up the 2s and 2p orbitals, and the atoms before carbon, especially beryllium and boron, for which you are going to see these exceptions, are like, hey, I am small enough, I might not need the 8 electrons. So they can have less than an octet sometimes. All right, what happens when we are expanding the octet rule? What is the case when we actually can have more than 8 electrons around the central atom? Well, we need more space for that, right? In the second period, we only have 8 spots in the 2s and 2p orbitals. However, in the third period, right here, so starting from the third period, we are actually filling up the 3s and the 3p orbitals, and we have the 3d orbitals right there as a space where we can put extra electrons if we need to do so. So if we have, for example, a central atom phosphorus, it's like, hey, I'm filling up my 3p orbital, I'm going to have the 8 electrons, but if you give me more, I can still rent out my 3d orbital and put those extra electrons there. It's just kind of like Airbnb or a vacation home. Hey, I can put my electrons there. I have space. But in the second period, there is no empty d orbital where to add the extra electrons. So actually, carbon, nitrogen, oxygen, fluorine, including neon, we are never going to see those elements expanding the octet rule. For carbon, nitrogen, oxygen, and fluorine, we are always going to have 8 electrons around them in a Lewis structure. Okay, I hope this makes sense. Let's take a look at some examples, and let's use the formal charges to actually figure out which Lewis structure is more correct. Let's start with beryllium dichloride. So that is BeCl2. If you look at the periodic table, beryllium is right here, chlorine is right here. So we are going to have 2 and 7 valence electrons respectively. So 2 plus 2 times 7, we are going to have a total of 16 valence electrons. Beryllium is the central atom. We are going to use 4 electrons to draw the single bonds. So minus 4, we still have 12 valence electrons left. And I can satisfy the octet rule for the chlorine atoms by adding the remaining 12 electrons. All right. Now, I would say normally that, hey, my beryllium might be unhappy because it doesn't have the 8 electrons around it. But remember, beryllium is tiny. It doesn't always want the 8 electrons. So let's take a look what would happen if we would actually satisfy the octet rule. We would have the beryllium atom again in the center, the 2 chlorine atoms on the side, and we could draw a double bond from each chlorine atom to satisfy the octet rule for beryllium. Now, let's check the formal charges and see which one is more correct. We need to have the valence electrons and subtract from that the electrons assigned to the atom in the Lewis structure. So the sum of the non-bonding plus half of the bonding electrons, or as I like to call it, the sum of the sticks plus stones around the atom. Okay, so for chlorine, we know that we have 7 valence electrons minus, let's count the number of sticks and stones. So 1 stick, 1, 2, 3, 4, 5, 6 stones, which is again a 7 a total. So we are going to have formal charge of 0. For beryllium, the number of valence electrons is 2 minus this 2 sticks around it. So that's gonna be a 0. And for the other chlorine, it's 7 minus 7 again, which is going to give us a formal charge of 0. Now, what happens with the other structure? So there we are going to have 7 valence electrons for chlorine again, minus 1, 2, 3, 4, 5, 6. So that's going to give us a plus 1 charge. For beryllium, 2 minus 1, 2, 3, 4. So that's going to give us a minus 2 formal charge. And for chlorine, 1, 2, 3, 4, 5, 6 again. So 7 minus 6 is going to give us a plus 1 formal charge. Okay, does this make sense that actually the chlorine atoms would have positive formal charges around the negatively charged beryllium atom? No, it doesn't, because actually chlorine has a higher electronegativity than beryllium. So chlorine will pull away the electrons from beryllium. So it's impossible to have a negative formal charge on a less electronegative atom in this structure. So actually this structure is incorrect. And the first structure is going to be the correct one. Moreover, in that one, the formal charges are closest to 0 in each atom. So remember, always check the electronegativities of the atoms, okay? And make sure that you are going to have the negative charges on the most electronegative atoms. Let's do another example. So one of my favorites is the phosphate ion, which is PO4 3 minus. Let's check the number of valence electrons. So phosphorus is here. It's going to have 5 valence electrons. Oxygen is here. It's going to have 6 valence electrons. So 5 plus 4 times 6 plus 3 for the charge is going to give us a sum of 32 valence electrons. Now we need to start drawing the structure. So phosphorus is the central atom, and we are going to draw the bonds to the oxygen atoms. We used up in 4 bonds 8 electrons, so we still have 24 valence electrons to work with. When we can put those on the oxygen atoms, actually we need 24 in total, 6 times 4, because I have 4 oxygen atoms, to satisfy the octet rule. Alright, so I satisfied the octet rule for both phosphorus and oxygen. Now, what's up with the formal charges? If we look at the phosphorus atom, we know that it is going to have 5 valence electrons minus the electrons assigned to it, which is 1, 2, 3, 4. It's going to have a plus 1 formal charge. How about the oxygen atoms, where they are all the same, so I can just look at one of them. I know that I have 6 valence electrons in oxygen, minus 1, 2, 3, 4, 5, 6, 7. So I'm going to have a minus 1 formal charge. Does it make sense? It actually makes sense because oxygen is more electronegative than phosphorus. So this is a valid Lewis structure, but can I make it better by having formal charges closer to 0? Yes, I can do it. I can do it by adding a double bond to the phosphorus atom, which will violate the octet rule. But remember, phosphorus actually has the space to do it because it is in the third period, right? 1, 2, 3. So in the third period, there is already space to put the extra electrons on the 3d orbital. All right, I hope this makes sense. So now I can do the following. I have the phosphorus atom, a double bond to one of the oxygen atoms, single bond to all the other ones. Let's satisfy the octet rule for each oxygen atom. If we do that, we are going to put only 2 pairs on the double bonded oxygen atom. Don't forget about the 3- charge. Now, what happened to the formal charge of the phosphorus atom? So we know that phosphorus is going to have 5 valence electrons minus 1, 2, 3, 4, 5. So that's gonna give us a formal charge of 0. Yay, we are already winning. And what about the oxygen atom that has the double bond? This one, 6 minus 1, 2, 3, 4, 5, 6. So that's gonna have a formal charge of 0 again. So when we are comparing the two structures, actually the dominant structure is going to be this one, the second one, because it's going to have the formal charges closer to 0, with the phosphorus having a 0, this oxygen atom having a 0 formal charge, and all these other oxygen atoms still having a -1 formal charge. Now let's just take a look at the sum of the formal charges. So when we add -1 to -1 to -1 plus 0 plus 0, we are going to end up with 3 minus. So that is going to happen in every single case because the sum of the formal charges should give us the charge on the overall molecule or ion. Okay? All right, now a question. How many resonance structures does the phosphate ion have? And actually going to have 5 different resonance structures. Why? We're going to have the first one, this one, which is a valid Lewis structure. However, it is not as stable as the Lewis structure, which has the double bond towards the phosphorus. So the first one is going to be a minor contributor, and it's going to be less stable than the second resonance structure. And where are the 3 more resonance structures? Well, I can move around the double bond from here to here to here to there, which is going to give me a total of 5 different Lewis structures. So notice that this one here, where we only have single bonds around the phosphorus atom, is a minor contributor. However, it is still a valid Lewis structure because we do not have negative charges on atoms that are less electronegative than the other ones. And these other 4 resonance structures are just the same structure moving around the double bond or the placement of the electrons. All right, I hope this makes sense. See you in the next video.